At an altitude of nearly 10,000 meters, a modern airliner cruises through the sky at almost 900 kilometers per hour. Thousands of passengers sit comfortably inside. From the ground, the aircraft appears to glide effortlessly above the clouds. But hidden behind that smooth flight is a constant battle against one of nature's most powerful forces: air resistance. Every second, the aircraft pushes through an invisible wall of air. Its engines burn enormous amounts of fuel just to maintain speed and altitude. For airlines around the world, fuel represents one of the largest operating costs. Even a tiny improvement in efficiency can save millions of dollars every year. If you look carefully at the wing of a modern airliner, you may notice something unusual. The wing does not end in a straight line. Instead, its tip bends upward toward the sky. At first glance, it seems like a minor design feature, a small detail that couldn't possibly make much difference. Yet airlines spend millions of dollars installing these curved tips. Some carriers even send aircraft back to maintenance facilities years after purchase to have them added. Why? Why would companies invest so much money in such a small piece of the aircraft? The answer lies in a hidden problem that exists on every airplane wing. A problem powerful enough to waste fuel, reduce efficiency, and affect the entire aviation industry. To understand it, we first need to understand how a wing creates flight. The principle of flight is surprisingly simple. An airplane flies because its wings create a difference in air pressure. As the aircraft moves forward, air flows around the wing. Pressure beneath the wing becomes higher. Pressure above the wing becomes lower. This pressure difference generates lift, allowing the aircraft to rise into the sky. But nature constantly tries to restore balance. High-pressure air always wants to move toward low-pressure areas. And at the tip of every wing, that opportunity appears. Dense air from beneath the wing rushes upward toward the lower pressure region above it. This movement creates a powerful rotating vortex, an invisible tornado of air. These wingtip vortices can extend for kilometers behind an aircraft. Although passengers cannot see them, they have a significant effect on performance. The vortex steals energy from the wing. It creates what engineers call induced drag. In simple terms, the aircraft is dragging an invisible brake behind it wherever it flies. The engines must work harder to overcome this resistance. More thrust is required. More fuel is burned. And operating costs increase. For decades, engineers searched for a solution. If they could reduce these vortices, they could dramatically improve aircraft efficiency. The challenge was finding a practical way to do it. The earliest solution seemed obvious. If vortices form at the wingtip, why not move the wingtip farther away? Engineers proposed building much longer wings. In theory, longer wings would reduce the strength of wingtip vortices and improve efficiency. The mathematics looked promising. Unfortunately, reality had other plans. Longer wings created enormous structural problems. Imagine holding a ruler from one end and pressing down on the other. The longer the ruler becomes, the greater the force acting on its base. Aircraft wings behave in a similar way. As wings became longer, the stress at their connection to the fuselage increased dramatically. Turbulence could place enormous loads on the structure. To keep the wings strong enough, engineers would need to add large amounts of reinforcement. That meant extra weight. And extra weight would cancel many of the efficiency gains. There was another problem. Airports. Wider wings required more space. Aircraft could struggle to fit existing gates, taxiways, hangars, and maintenance facilities. Rebuilding airports around the world would be incredibly expensive. The aviation industry needed another solution. something that could reduce wingtip vortices without dramatically increasing aircraft size. The answer would come from a surprising source, not from a laboratory, not from a wind tunnel, but from nature itself. By the 1970s, aviation engineers had reached a dead end. Longer wings created structural problems. Simple vertical plates added drag and introduced dangerous vibrations. The industry needed a completely different approach. One man decided to stop looking at aircraft and start looking at nature. His name was Richard Whitcomb, an engineer working at NASA. Whitcomb believed that nature had already solved many of the problems engineers were struggling with. After all, birds had been flying efficiently for millions of years. If they could travel vast distances while using minimal energy, perhaps they held the answer. He began studying large soaring birds such as eagles, hawks, and vultures. What he discovered was fascinating. These birds rarely keep the tips of their wings perfectly straight. Instead, the outer feathers spread apart and curve upward toward the sky. At first glance, this appears random, but in reality, it is a highly efficient aerodynamic design. Each feather helps break a large vortex into several smaller vortices. Instead of one powerful swirl stealing energy from the wing, the airflow is divided into multiple weaker streams. The result is less drag and greater efficiency. Nature had already found a way to control wingtip vortices. Now, engineers needed to adapt that solution for aircraft. Inspired by these birds, Richard Whitcomb developed a revolutionary concept. Instead of attaching large flat barriers to the wing, he designed a small vertical extension that curved upward. He called it a winglet. Unlike earlier concepts, the winglet was not simply a wall-blocking airflow. It was a carefully shaped aerodynamic surface. Its curved profile allowed it to interact with the wingtip vortex in a completely different way. As the vortex moved around the wingtip, it struck the winglet at an angle. This interaction generated a small amount of lift. But unlike the lift produced by the main wing, part of this force pointed forward. In effect, the winglet recovered energy that would otherwise be wasted. Instead of allowing the vortex to become pure drag, the aircraft could now reclaim some of that lost energy. It was a remarkable idea. Rather than fighting the vortex, the winglet used it. The aircraft's greatest aerodynamic enemy became part of the solution. Initial wind tunnel testing produced extraordinary results. Engineers measured significant reductions in induced drag. Fuel efficiency improved. Aircraft performance increased. And all of it came from a relatively small modification at the end of the wing. But laboratory success does not always translate into real-world success. The next challenge was proving that winglets could work safely on full-size aircraft. The aviation industry was cautious. Airliners carry hundreds of passengers. Every modification must meet extremely strict safety standards. Engineers needed to know exactly how winglets would behave during real flights. Special test aircraft were equipped with prototype winglets. Researchers conducted extensive flight trials. Some tests used smoke generators to make airflow visible. Others relied on sophisticated sensors and cameras. The results exceeded expectations. The enormous wingtip vortices behind the aircraft became noticeably weaker. The turbulent wake dissipated more quickly. Induced drag was reduced. Fuel consumption dropped. For the first time, engineers had practical proof that the concept worked. The implications were enormous. Every percentage point of fuel savings could translate into millions of dollars for airlines. And unlike building an entirely new aircraft, winglets could often be added to existing fleets. Suddenly, airlines around the world became interested. What began as a NASA research project was about to transform commercial aviation forever. Winglets solved more than just a fuel problem. They also helped reduce one of aviation's lesser-known hazards: wake turbulence. Every aircraft leaves a trail of rotating air behind it. These invisible vortices can remain in the atmosphere long after an aircraft has passed. For large aircraft, the effect can be extremely powerful. A smaller airplane flying through that disturbed air can experience sudden rolling forces and loss of stability. Because of this danger, air traffic controllers must maintain separation between aircraft during takeoff and landing. Larger aircraft require even greater spacing. This limits airport capacity and can contribute to delays. By reducing the strength of wingtip vortices, winglets help weaken wake turbulence. The dangerous air behind the aircraft dissipates more quickly. This improves overall safety and contributes to more efficient airport operations. A small aerodynamic improvement was producing benefits throughout the entire aviation system. And the story was only beginning. Once airlines saw the benefits of winglets, they wanted them immediately. There was only one problem. Most commercial aircraft had already been built. Waiting years for entirely new aircraft designs was not an option. Airlines wanted winglets installed on aircraft already in service. At first, this seemed straightforward. Simply attach the new structure to the wingtip and begin flying. In reality, the task was far more complex. The wing of a modern airliner is not a simple piece of metal. Inside are fuel tanks, hydraulic systems, electrical wiring, and structural components designed to handle enormous loads. Adding a winglet changes how forces are distributed throughout the wing. Even though the winglet appears small, it increases bending forces at the wing root. To ensure safety, engineers had to reinforce internal structures, strengthen key components, and carefully recalculate aerodynamic loads. Many aircraft underwent extensive modifications before receiving certification. The process required thousands of engineering hours and rigorous testing. Yet airlines considered the investment worthwhile. The expected fuel savings would quickly repay the cost of installation. The aviation industry had found a rare opportunity, a relatively small upgrade capable of generating enormous long-term benefits. Today, winglets are among the most successful aerodynamic innovations in aviation history. The numbers tell the story. Depending on the aircraft type and operating conditions, winglets can reduce fuel consumption by approximately 4 to 7%. At first glance, that may not sound dramatic, but aviation operates on a massive scale. A single commercial aircraft can consume thousands of tons of fuel every year. Multiply that across thousands of aircraft flying every day around the world, and the savings become extraordinary. For major airlines, even a 1% improvement in fuel efficiency can save millions of dollars annually. Winglets often save far more than that. Collectively, they have helped airlines save billions of dollars over the past several decades. A design feature only a few meters tall has become one of the most valuable investments ever made in commercial aviation. The advantages extend far beyond economics. Every kilogram of fuel saved means fewer emissions released into the atmosphere. As airlines worked to improve environmental performance, winglets became an important part of the solution. By reducing fuel consumption, they also reduce carbon dioxide emissions. Across the global aviation industry, this translates into millions of tons of avoided emissions every year. Passengers rarely notice these benefits while sitting inside the cabin, yet every flight equipped with winglets contributes to a cleaner and more efficient transportation system. there are operational benefits as well. Reduced drag can improve climb performance. Aircraft may be able to fly farther without refueling. Some routes become more economical, and airlines gain greater flexibility in how they operate their fleets. What began as a solution to a small aerodynamic problem ultimately improved multiple aspects of aviation. Technology never stands still. The original winglets designed by Richard Whitcomb were only the beginning. As computer modeling became more advanced, engineers developed new variations. Many modern Airbus aircraft use Sharklets. These elegant curved extensions resemble the fin of a shark and provide additional efficiency improvements. Boeing introduced blended winglets, designed to smoothly merge with the wing surface and reduce aerodynamic interference. Later came split-scimitar winglets, featuring extensions that curve both upward and downward. Some of the newest aircraft use highly optimized wingtip designs specifically tailored for their mission profiles. Although the shapes differ, the objective remains the same. Control the airflow. Reduce vortices. Recover wasted energy. Increase efficiency. Each new generation pushes performance a little further, a fraction of a percent here, another fraction there. In an industry where fuel costs are measured in billions of dollars, even the smallest improvement matters. The next time you sit beside an airplane window and look out at the wing, you may notice that familiar upward curve at its tip. It is easy to dismiss it as a simple design choice, a stylistic feature added by engineers. But the reality is far more remarkable. That small structure represents decades of research, experimentation, and innovation. It embodies lessons learned from physics, engineering, and even the natural world. The winglet transformed a costly aerodynamic problem into an elegant solution. It helped airlines save billions of dollars. It reduced fuel consumption. It lowered emissions. It improved safety. And it changed the way modern aircraft are designed. Perhaps most importantly, it reminds us that some of the greatest breakthroughs are not always the largest. Sometimes, a small detail at the very edge of a wing can reshape an entire industry. And as millions of passengers travel above the clouds every day, that simple upward curve continues to quietly make flight safer, cleaner, and more efficient.